Okay, so branch and bound refers to all state space search method in which all children of E node are generated before any other live node can become V node. Meaning is, so in branch and bound we will name the nodes. First is that live node, okay. Second is E node. Live node means the node which you should be. Now here this expansion term will come. That means like when you will be visiting the node will expand, okay, like this. So let's say initially 1 is live node and it has expanded to 2, 3, 4, 5 AI. Branch and bound has 3 methods. One is FIFO branch and bound, FIFO branch and bound, and then least cost branch and bound. In least cost branch and bound we can somehow map A star algorithm. That will. Branch and bound is a state space search method in which all the children of a node are generated before expanding any of its children. That means if you have this one, the node will be expanded. This is live node. This is live node. Its node will be expanded, and then when next time node will be expanded, it will like this node will be expanded, then this node will be expanded, then this node will be, whichever is very good. This is the actually definition live node. A node that has not been expanded, a node are generated before expanding any of its children. Okay, so let's say if I am expanding 2 is the live node. If I am expanding 3 is the live node, and like that it will happen. Okay, so this is live node. Live node is nothing, just they named it. We did same thing for other strategy like this expand. Expand mean will further goes and we'll see which are the adjacent. Basically this node 1 has 4 adjacent node, and then when node 2 will be expanded, it will be assuming that 2 will be having some adjacent node, like that things will go. And then there is called E node. E node is the live node whose children's are currently being generated is called a live node. The live node and whose children are currently being generated are called E node. Currently being generated are called E node. Actually E stands for expansion or expanded node. So this is live node, this is expanded node, which is already generated, which is called expanded node. And another type of nodes are there which is called dead node. So dead node, also this terminology I have used during other techniques, which is called a node that has been expanded further and it has no chance of expansion, further expansion. So that is called dead node. Okay, so dead node, if solutions you are getting, you will say the dead node is giving the solution. Otherwise, if solutions are not available, you will say dead node is not giving. Further expansion is not possible for dead node. So this is what branch and bound method. Okay, and these are the few nomenclature. Now 3 types of branch and bounds are there. First branch and bound is called FIFO branch and bound. Now I will be asking questions because stack is over. Your favorite topic, stack. First out. So which data structure follows first in first out? Q follows first in first out. That is actually the drawback of stack, because in stack what happens, you let's say element 1, element 2, element 3, you push and then the element 3 has come at the end, but while popping you are popping this element 3 first. So this is the drawback. That means you are not giving the due credit. That is the drawback of stack. That has been eradicated in Q, where you say that if element 1 has come first, then element 2 has come second, element 3, this element 1 will be deleted first. E has come first, it will be deleted last. So that means first in last out. Sometimes it is called stack I am talking about, and this is Q, and sometimes it is called last in first out also. LIFO structure or philo structure, both are same for stack, and this is the drawback. But in case of Q, whichever the element come first, it will be deleted first. So Q is both ends are open in case of Q. The end I am telling, rear pointer is the pointer which helps you to insertion, and front pointer are the pointer which helps you to deletion. So initially both the pointers in -1 means the Q is empty. Then let's say one element. So let's say one element will be inserted in the Q. So initially front pointer and rear pointer both are -1 means Q is empty. If you insert one element here, so front pointer, both rear pointer will be maybe initialized to 0, -1 to 0 it will go, and then further rear pointer will increment. So here it will come like that, things will happen. Okay, front pointer also will increase. But rear pointer will increment, front pointer will be here only. Next time E2 insert here, but if you want to delete it, you have to delete E1 first. So that is the catch of Q. In case of FIFO branch and bound, first in first out technique will be used, and first in first out technique, and this first in first out obviously will be using Q data structure, or you can better call it Q like data structure, not exactly Q but Q like data structure. That means the element which will be expanded first, chances of that it will be deleted first. That is the meaning. So this is Q like structure, or Q you can call. Whereas, and in a broader perspective, you can call FIFO structure based, actually this searching algorithm actually follows BFS. What is the full form? Breadth first search. Breadth, these are there in data issue. So breadth first search. This breadth first search guy, what it does, these two searching algorithms, one is breadth first search, another one is depth first search. Depth first search. Both are conceptually totally different. Breadth first search sees, both techniques sees the adjacent vertices first. This depth first also see which are my adjacent vertices. Let's say this is the start node and this is the start node. Okay, these both are start node, but in case of breadth first search, I will see who are all my adjacent vertices. Level by level I will check them. Here when I start, in case of depth first search, same thing will happen. First I will check who are my neighbors, immediate adjacent vertex, I will do that. But afterwards there is no neighbor business. Then I will go deeper to the node. In case of depth first search, I will go deeper to the network, that means deeper to the tree. But in case of breadth first search, this fellow always search like this. First it will search this, then it will search this. In case of BFS I am talking, and then it will search this. Once this level is this level, full expansion happen, full invigilation happen for this node, this node, this node. This guy will again further expand. Then it will search this, then it will search this, and then this. That means level by level it will search. In case of breadth first search, very fundamental searching algorithm which are available in data structure as well as in algorithm analysis. But in case of depth first search, okay, in case of LIFO, this is called LIFO branch and bound. In this case, we will be using depth first search. We will be using depth first search. Okay, so both we will see. So in case of depth first search, what will happen? First, you will see who are the neighbors. This is the neighbor. You will come here, and then you will further check this, and then like that you will go this, like that you will go. So you are going deeper to the node. This node you won't check this node, and then what are the other adjacent vertices you won't check. You will check deeper to the node. So this is DFS, this is BFS, fundamentally different. Both are efficient algorithm. Okay. So in this case, FIFO branch and bound, we will see how this FIFO branch and bound use Q like data structure, use BFS like searching algorithm, and solves the problem of 4 queen problem. How inside n queen problem, how it solves, we will see that. Okay. So any doubt up to this mics are this one you can take, no problem. So we have a Q here. Q follow first in first out data structure. So here you see this is the given graph or tree, whatever you say. How the movement happened. So initially this is S. So S you can in NQS in the Q. Sorry, this is S. You can NQS in the Q. You have to see who are the children of Q. I mean children of S, 1 and 2. So what you will do, you can actually before enqueuing another element, you delete S and print it here, and then you can further insert here, because let's say why I am deleting, you cannot delete also, no problem. Once you delete means it has expanded. Let's say like that angle I am telling. So the expanded S has been deleted, and then you have 1 and 2 whose immediate neighbors, adjacent vertex 1 and 2. So then you into the rule, you have to expand this and you have to expand this, level wise we will go. So once you expand, then this also will be deleted. So 1 has been S, then 1, then once again 3, yes, 3 has to come here, because once you expand who are 1 children, 3, so 3 has been enqueued in the Q. Okay, then 2 has to be deleted, 2 has deleted. Once you delete 2, who are the adjacent 4? 3 already is there, so no need. So 4 is there, so you once you delete 2, then you can insert 4 here. Then you delete 3. Once you delete 3, it will be, who is his children? 5. So 4 and then 5. And then if you delete 4, nothing is there. And okay, 3 and then 4 and then finally 5 will be deleted. This is breadth first problem or 4 queen. So we have a n queen problem already we have solved, right? Other method. Yeah, 4 cross 4. 4 queen actually. That can be further extended to n queen. 4 cross 4. Now we are going to make FIFO branch and bound technique. FIFO branch and bound technique. Okay. FIFO branch and bound technique. What we are going to do? First we are going to see. First, this is a state space tree is must. State space tree is must in every cases. Even in backtracking, everywhere state space tree is must. So what we are going to do? First we are going to insert Q1, queen 1. So what you can do? Queen 1 if you place. So this is my state space tree T first node. Okay. So how many options are there for every queen? 1, 2, 3, 4. So let's say initially we are going to place Q1 in row. Okay. Let's say I am placing queen Q1 at these positions. First column. So queen Q1 in column 1. How many options I have for queen Q2? Queen. Now we look this problem from column point of view. In case of backtracking or not backtracking, we did row wise. Here we look at the column. How many way I can place queen Q2? Can I place queen Q2 2? I cannot place queen Q2 in column 2 because attack. One second, ma'am. Here you see, here this part you forget. This is not. So column Q. This is column 2. This is column 1. This is column 3. This is column 4. No. Column wise I am saying this column, this column, this column. I cannot place it here, right? So that means let's say here queen Q2. This is 2. This is let's say 4, 5, 6. This is actually not an answer. I cannot place it. Okay, column 2, which you can write, sir. Please come, sir. X2 equal to 2. Can I place queen Q2 here? Yes. So I can place it. So this is good sign. So this is 7. Q2 equal to 3. I can place. So this is somewhat a good. It will give us result. Do it, sir. Yeah. Oh, okay. Now can I place queen Q2 at column 4? Yeah, I can place it. So that it won't attack queen Q1, right? Here, if I place queen Q2 here, if I place queen Q2 here, that also won't attack queen Q1. It won't attack. So I can place it here. So this is 8. X2 equal to 4. Okay. Now, right? Intention that I am trying to see first row, second column, third column, fourth column. I am able to push or not. So, yeah, column wise will go. But see here, row wise, if you go means it will create chaos. No, you won't able to track the rows, which rows you go. You can put anywhere. We have the solution in back. You can call it that row 1. We have placed queen 1 in column 1. Then we are going to see column 2, column 3, column 4, but it is second row. Yeah, in that aspect it is second row. Okay. So here I can place one queen Q2. Here also I can place queen Q2. So this is one of the option that I have. This is one of the option I have. If I would have placed queen Q1 in okay, if would have placed this thing instead of just, I'm telling you just little bit. We are going to place queen Q1 in column 2. That means I am going to place queen Q1 here, this fellow. This is over, sir. This is over means we'll see next also. We'll see. But as I said, this for a very interesting question you asked. That means you are understanding. BFS brute force search. Level by level it will go. First level, this fellow has been explored. Okay, it has explored. It has got children. This is first child, second child, third child. Shall I go here? No, I won't go here because level by level, as I said, it will follow BFS. Just now I showed. So first, this node I'm going to explore, these three. So what I'm going to do, I'm going to put X1 in position here, this position. Okay. So for this, if you put, then how many options I have? This column to already it is out of the scenario. So can I place Q? Sorry, this is Q1. This is Q1. This is Q1. Can I place here? No. So just make it here. X2 equal to 1. I cannot. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. I cannot place it here. This is a wrong things to go. Can I place it here? No, no chance. Can I place it here? Q2. Let's say here. No, I cannot place it here also. So this is X2 equal to. This is okay. So how much I wrote? X2 equal to 3. No, this one 3. 3 not possible. So this is 10. Okay. This is. Huh? For 3, for this one, that is earlier one, Q1 here. Now Q1 has been shifted to here. If you would have pushed Q1 here, then what would be the scenario? So for this is also not possible. This is also this means 3 if I place here. This is 3. That is also not possible. If 4 if I placed Q2 equal to 4, that could be a solution, which is 11th number. Okay, this is done. So similarly, you have to find. So if let's say if I would have placed Q1, so this is also not my answer. Let's say I would have placed Q1 here. I would have placed Q1 here. That means so now X1 equal to 3. Once you place here 3, then which other option can I place it here? I think I should little. No. So a lot of failures are there. Which is the correct answer? We'll see. So just I won't do whole 3. We'll see. I will do the whole 3. Okay. So here X3 equal to 3 here. Then what will happen, sir? Which are the option? Can I place Q2 here? Yes, I can place. So this is X2 equal to 1. This is 12. Then X2 equal to. Can I place it here? No, I mean this could be a solution. This could be a solution at level 2. If you say this is level 1, this is level 2. In level 2 it seems like that, but we have to place 4 queens now. So it will go the state space. So here it is 12, then it is 13. So this is also not possible at this is 1, then this is 2, right? 1 is possible, 2 is not possible. 2 is not possible, and 4 is not also possible. Very good, ma'am. 14, 4 is possible. At this level it is possible. 4 is also not possible. Correct. 4 is not possible. So only this one could have given at level 2. You are thinking that okay, if you if you move X, if you put first thing as 3, queen 1 in 3, then queen 2 in second column, first column, then you have a chance, first row, then you have a chance that you might get answer in the future. No attacking is happening, right? Similarly, for the fourth queen also you have to do the stuff. Once you do this, then you have to again expand this. Yeah. Now we have to place after queen 1, Q1, Q2, you have to check Q3. So if you have the whole state space tree, you will find this like this is the state space tree. Okay. So if you see that this also, like in this case, we thought that this guy can give answer, but this fellow also, once you move further, it will also not give any answer. So basically you have answer here. At 31st insertion, you will be having an answer. So answer will be like this, and this. Only one answer for 4 queen problem using branch and bound method. That means branch and bound method means what? We have branching and we have bound also. Actually the answer, okay students, today we are going to see how branch and bound method can be helpful for 0-1 knapsack problem. Branch and bound method can be helpful for solving 0-1 knapsack problem. Reading this, when we are solving this 0-1 knapsack problem, this fellow also give 2 to the power n. This guy also give 2 to the power n time complexity, provided there are n number of nodes in the tree. and this brute force also gives 2 to the power n. Then what is the significance that I should be learning these 3 methods? Where is the need? Why should I need to learn backtracking solution for the 0-1 knapsack? Why should I need branch and bound? Why should I need brute force? In fact, why should I need dynamic programming? Dynamic programming time complexity could be little bit less than these 3. You go and read more. Again, I'm just repeating the problem. What is 0-1 knapsack problem? Whether thief, we have these gold I got. So gold items are there. Thief has come and he wants to rob the bank. Whether he should take this or he should leave it. So if he leaves it, then it is called 0. If it takes, then it's called 1. 0-1 knapsack problem. So already we found that dynamic programming could be a solution. And what do you think? What about greedy method, students? Is it a good solution for 0-1 knapsack problem? Greedy method, just a recall. For greedy method, it's also not providing good solution for 0-1 knapsack. Greedy method provides good solution for fractional knapsack. Amruta and the other one, Sanjukta, no, your name? Huh? Why don't you come at the front bench? We'll be talking, it will be problem for me to, no. Okay, so if it is fractional knapsack, your CGP also not good. I have checked. Both of yours failed in couple of subjects. Fractional knapsack. Okay, for fractional knapsack, greedy method is somewhat good solution. That means when you are allowing this gold item to be partitions and fraction, dust, gold dust, then greedy method is somewhat good solution. So questions can be asked whether greedy method is good for 0-1. You have to say no. This is a very common question. Whether greedy method is good, dynamic programming is good for 0-1. You have to say yes, somewhat better. Whether branch and bound and brute force and backtrackings are good for fractional knapsack, you have to see. Okay, so these things are there. 4 or 5 solution mechanisms are available. Okay, greedy, then backtracking, then what else? Branch and bound, and then the most worst is the brute force. So you have 1, 2, 3, 4, 5, 6 methods you are applying for the same problem. There must be some advantage. So anyway, so 0-1 knapsack problem is that only. Okay, so you have a knapsack of W, capital W, which is the size of the knapsack. That means the bag, and the thief has to take this item or he has to leave it. That is the final problem statement. Okay, so basically brute force method, just now I told you that this approach would give us solution. It is of exponential time complexity, 2 to the power n, and in all the cases we have the formulation of the tree which is of binary tree. Now you can ask me, sir, whether trinary tree is also possible. It is possible. Nobody has think about it. But the next method we are going to see branch and bound method. Branch and bound method. So next we are going to see branch and bound method for job assignment problem. Next, we are going to see branch and bound method for job assignment problem. So, what is job assignment problem? In a standard version of job assignment problem, there can be n jobs, okay, and n workers. These are the workers A, B, C, and there are n jobs. So, we can assign any of the available jobs to any worker. The condition that a job is assigned to the worker, the other workers can't take that particular job. So if we assign, let's say, job 9 to A, job 1 to A, then and let's say the 9 is the cost or minimum cost. So that job cannot be assigned to any other worker. So once a job is assigned to a particular worker, same job cannot be assigned to any other worker. So here our main aim is to complete all jobs by assigning one job to each other in such a way that sum of the cost of all jobs should be minimum. So basically it's a minimization problem. Minimization problem. So basically this is optimization problem, and it comes under minimization problem because we have to find the minimum cost after assigning all jobs to all worker. Cost should be minimum. So these all numbers that are provided in the table are cost. What is the cost of assigning job 1 to A is 9. Cost of assigning job 2 to A is 3, like that. So this is the algorithm. This algorithm job assignment problem using branch and bound. Here we are using branch and bound, and the detail of branch and bound already we have discussed. We have to make a state space tree here. State space tree. So minimum cost we have to find. That is the main thing. And so here AMI, this matrix, minimum cost matrix, matrix is the input cost matrix. This one contains information like the number of available jobs, of available workers, etc., and the associated cost of each job. The function mean cost maintains a list of active nodes. Mean cost maintains this is a function basically, and this is the matrix. This function maintains a list of active jobs. The function list cost, this one, calculates the minimum cost of the active nodes at each level of the tree. So as state space tree will be generated at each level, minimum cost of the active nodes are getting generated by this least cost function. After finding the node with minimum cost, we remove the node from list active and return it. And then add function in the pseudocode which calculates the cost of a particular node, adds it to the list of the active nodes. Okay, and each node contains some information such as cost, total number of jobs, as well as the total number of work. So let's see. Let's take an example. Let's take an example. Let's say we have 4 workers. Corresponds to 4 jobs. Okay, 4 workers correspond to 4 jobs. Let's say this is job 1, job 2, and these are the workers, A or B. 4 workers are there. Let's say values are, the cost is 9, seven. Each worker choose job with minimum cost in the list of the unassigned job. That you have to remember. So each worker choose job with minimum cost from the unassigned job. So the job which is already assigned cannot be chosen.
And here you have to make a state space tree. State space tree. We have to find, initially you have to find lower bound, and then you have to find the upper bound also. So one thing you have to remember, that the minimum cost cannot surpass the lower bound. Initial minimum cost cannot surpass the lower bound. So what we will do initially, take the minimum value from each row. So from row A, minimum value is 2. You can see that from row A minimum value is 2. Row 2 minimum value is, row E minimum value is 1, and D minimum value is 8. So this comes around 10. So the lower bound, initial lower bound is, this you have to remember, initial starting point. Okay. So what will happen? Let's say if worker A choose job 1, then what will be the cost? So if A choose job 1 means definitely this is the first entry, so 9 will come here. Once 9 comes, this will be logged. Okay, so from job 1, this 9 he has chosen because this is the first entry. For job 2, choose the minimum one, it is 4, because 2 cannot come, because once you choose 9 means this whole row will be blocked, whole column will be locked. So 4 it can choose, from the remaining it, and then from here minimum is 1, then finally minimum is 4. So the, for when A choose job 1, the job 1 assigned to A, cost become 18. If A chooses job 2, then what will happen? Job 2 means immediately 2 will come, and then in that case just that you have to write. Okay. Here we have 2, right? Once you choose 2, that means this row and this whole thing will be logged. Okay, so from here it is chosen 2, so 2 will be there. Job 2, A choose job 2, or job 2 is assigned to A, then 2 plus, from here 9 will be also be logged. So if you choose 2 means situation is something like this. So this 9 will go. So here from job 1 minimum is 5. 5 will be chosen. From here minimum is 1. From here minimum is around 12. Similarly, this is A equal to 2. Similarly, for A equal to 3. Okay. A equal to 3. A equal to 3. This is this one. So this and this will. Okay, so 7 will be definitely coming. From here, from job 1 again 5, job 2 again it is 4, and job 4 again it is 4. This total cost is 20. Okay. Now for the same thing, same we have to do for, if job 4 is chosen or job 4 is assigned to A, then it will be 8. Sorry, yeah, 8. Definitely 8 will come first. Then here it will be like once 8 comes, 5. The job 1 it is 5. Job 2 it is 4. Job 3 1, which comes around 18. Out of this, we can see that minimum is 12. So 12 will be chosen. Branch and bound method, minimum is 12. 12 will be chosen. This node will be further expanded. Branch. So branching will happen here. Branching will happen based on the minimum cost. 12. This is 20. This is 18. And this is also 18. So 12. So here for B, we do means for B equal to 1. So if job 1 is assigned to B. Now A has done. We go to B. Now job 1. So it is like for now it is now B is assigned to job 1. Then what will happen? B this one. So 6 will be chosen. Then 2 is free. 6 means this one. From here. Earlier this was not available because job was occupied. This worker A was assigned job 2. Now 2 is available. So plus 2. From here it is plus 1. Plus 4. Which comes around 13. And next, when B is assigned job 2, is so job 2 cannot be taken because job 2 already has been this 2 has all we have chosen this one, right? Because of the job 2 already chosen. A has been chosen job 2 and then further expansion happens. So job 2 cannot be taken. So it's already assigned to A. Better we'll choose job 3. Job 3 means this one. So obviously 3 will come. Then here from job 1 it is 5. Job 2 it is, and for job 4 it is 4, which comes around totally 14. And then finally if it chooses this one, B equal to 4 also possible. In this case it will be 7 plus 5 plus 1 comes around. So this is my tree, and then finally for job 3 you have to go. Now this is, I hope you have done this. Just go to the next. Basically we have situation like this. B equal to 10, lower bound. Okay. Lower bound, and then A1 18. A2 12 and A3 20, A4 18. This is the first time when, and then we assigned job 2 to A. Then we have this B1 13. Sorry, this is yeah, B equal to 1. B equal to 2 not possible, so B equal to 3, which comes around 14. Equal to 4 comes around 15. Okay. Now which one is the minimum? This is the minimum one. 13 is the minimum. Is the minimum, so we will choose this one. So branching will happen here. Because these all are not following the bounding values, it is deviating because these are all maximum values. Then 13, 14 is maximum greater than 13, and 15 also greater than 13. So you won't choose this thing. So once this, so job 1 has been allotted to B, job 2 has been allotted to A. For C, what are the options we have? So A has been assigned to job 2 already, and B has been assigned to job 1. So C, for C option is either it will be assigned job 3 or for D job 4. This is one option. Another option could be A2 B1 is already there. C could be either 4 or D could be either the options. So if it is A equal to 2, A equal to 2 means the minimum is 2, that we have to write here. And then B equal to 1, B equal to 1 6, that also we are confirmed, it is already fixed. C equal to 3, C equal to 3 means this job. Okay, C equal to 3, which comes, C equal to 3 means this one, 1 here, plus B equal to 4, B equal to 4, we'll put it here 4, which comes around 13, and this one 6 8 comes around 19. Calculate this will come 19. So again, this is now C3 D4 already assigned. A job 2 has been assigned to A, job B has been assigned job 2 has been assigned to A, worker A, job B has been assigned to worker 1, job 1 has been assigned to worker B, job 3 has been assigned to D, and this is 1. So 4 jobs already have been allocated, so nothing much we can do, and we got the minimum thing. Okay, so further this thing is not possible, further branching is not possible because it is already fixed, all jobs have been assigned. Okay, so okay, this is the situation. So this is the lowest cost, and upper bound we started with 10 initial upper bound, and now we get upper bound lower bound we started with 10 lower bound, and upper bound we are getting here 13. The maximum cost would be 13, lower bound is 10. Okay, so this is the situation. So this is the lowest cost, this is the answer. So basically what happens, at level 1 we have ignored all the assignments, only we assign job 2 to 1. Then at level 2, we have ignored all the other assignments. We have assigned job 1 to B and worker B, and then finally job 3 to C and job 4 to D. And this is the final solution. This solution is the, so here the lower bound is started with 10 and upper bound is around, and total cost is, that is also 13. Okay, so this is called job assignment problem using branch and bound. Okay, another important thing is that time complexity is m into n. That means order of the matrix. Space complexity is %. So hello everyone. So next we are going to see how branch and bound method, which is an extension to brute force method only, can help us solving 0-1 knapsack problem. So 0-1 knapsack problem already we have seen in greedy, using greedy method we have solved 0-1 knapsack problem. It can also be solved by dynamic programming. But today we are going to see how branch and bound method can be helpful here. So let's assume that we have 4 items and thief is going to fill the knapsack. So the problem statement of knapsack problem, 0-1 knapsack problem, is that either thief will pick the gold item or he will keep it. He will keep it. So 0 means he is not choosing any item, any gold item, and 1 means he is choosing the item. So 2 options are always there: ignoring the item or choosing the item. There is no case of partitioning the item or breaking the gold item. That is called fractional knapsack, which you are not doing here. So here one thing is important. So there are 4 items are there, item 1, 2, 3, 4, and each item is having weight, value, and value by weight. That means per gram or per pound, how much it is, how much the cost of that item, so that you can understand the valuable item. And let us also arrange the items in terms of value per weight using descending order. That means the highest value according to the highest value, and then second highest value, like that will descending order will display it for the better solution. Okay, so it will be like a descending order sorting based on the value by weight. So you can see that item 1 weight is, let's say, 4 gram or 4 pound, and the value is $40. Similarly, like item 2 weight is, let's say, 7 pound or 7 gram, and cost is, value is $42, and then like that we have another item 3 and item 4s are also there. And there is a concept, new concept or new terminology that we are going to use here in all branch and bound method, which is called upper bound. So upper bound, so this is important. What is upper bound? The formula for branch and bound method for solving 0-1 knapsack problem, the upper bound formula is given like this, which is V plus capital W minus small w into Vi plus 1 divided by Wi plus 1. So this capital W is nothing but the knapsack size, maximum capacity of the knapsack. Small w is the item that thief is going to pick, and V is the value. Okay, so V is the value, which is in terms of $40, $42, $25. These are all values. So V plus W minus capital W minus small w, and Vi plus 1 divided by Wi plus 1. Now Vi plus 1 is nothing. If you are dealing with item 1, then you have to find ith plus 1. That means item 2 value by weight you have to find. If you are dealing with item 2, then you have to find item 3 value by weight. So if you are dealing with ith item, you have to find Vi plus 1. That means I plus 1th item divided by Wi plus 1th weight. That is how the formula is. So what we are going to do, we are going to make a state space tree, you can call it, or a recursion tree you can call. So initially you can see that the W equal to 0 because we haven't picked anything. Thief hasn't picked anything from the given items of gold. So it is initially 0 and the value also initial value is 0. Let's assume that the maximum capacity of the knapsack is 0. So upper bound will be how much? Initial upper bound. Just you have to put the value inside the formula. So initial value, because we haven't started yet, so it is 0. The capacity of the knapsack is 10 minus 0, we haven't picked anything, into Wi plus 1 divided by Vi plus 1 divided by Wi plus 1. That means you haven't started with anything and you have to find the ith. That means ith value is 0, but I plus 1, that means first element which is nothing but 10. 40 by W, this is Vi plus 1 and this is Wi plus 1. This is my ith item. I plus 1th item, and ith item to nothing we have picked, so that's why it is 0. But I plus 1 by Wi plus 1 is 10, which is this one. Okay, so if you find that, then it will be nothing but 100. So upper bound initially is 100. Then let's say it has picked, the thief has picked it has chosen the item 1. So item 1 value, weight is 4 and value is 40. So easily you can calculate weight is 4, value is 40. Item 1, let's say thief is choosing, and then upper bound will be how much? Similarly, V, which is 40, total capacity of the knapsack is 10, minus, because you have picked 4th, the first item weight is 4, 10 minus 4, which is equal to 6, is coming around 76. Upper bound is 76. Okay, and let's say, and then finally what will happen? So again in this side, let's say thief is not choosing anything. So W will remain W, small w will be, capital W will be 0, V will be 0, upper bound will be 0 plus 10 minus 0 into 6. This thing will be as it is, you have to replicate. If you don't choose anything, simply replicate it. But upper bound will change because this will be I plus 1, which is nothing but 6. This one, 6. Vi plus 1 by Wi plus 1. Okay, so it will be around 60 if thief doesn't choose anything. So let's say again this node will be expanded further. So if you pick item 2, if you pick already 4 is there, that means item 2, if you pick 7, 4 plus 7 equal to 11, and the value V will be 40 plus 42 because cost is 42, it will be around 82. But unfortunately 4 plus 7 is 11, which is more than the knapsack size. The maximum size of the knapsack is 10. So if it is 11, then no more further branching will happen. It will be dead end over here. It will become a dead node. No more further branching will be there. Okay, so this node is not going to be further expanded, but we can expand this node. If you pick the item, if you don't pick the item 2, okay, if you don't pick the item 2, this node can be fine. So if you don't pick the item 2, then you just replicate this thing as it is here. Only thing is that your Vi plus 1 by Wi plus 1 will change. So you are dealing with item 2, that means you have to check item 3 Vi plus 1 by Wi plus 1, which is nothing but 5. So here you have to write 40 plus 10 minus 4, which is as it is. Instead of 6, it will be 5 now. So which is around 70. 40 plus 30, 70. 40 plus 30, 70. So again, if you pick right side, it is you are choosing the item. Left side it is choosing the item. Right side you are not choosing the item. Thief is not choosing the item. So let's say it has again chosen item 3.
If in this case already 4 is the weight, and then third item it is picking, so third item weight is 5, so 4 plus 5 9, 4 plus 5 9. So this one, if you pick the value, if you now from here onwards you can see that if the thief choose the item 3, then 4 is already there, plus third item weight is 5, so 4 plus 5, which is equal to 9, and the value will be 40 plus existing value plus the value that is corresponds to the item 3, which is 25. So here it will be 40 plus 25, which is 65. And what will be the upper bound? Upper bound will be the current value plus 10, the knapsack's weight of the knapsack or the size of the knapsack, minus the weight that has been picked until now, which is nothing but 9. So 10 minus 9 into Vi plus 1 divided by Wi plus 1. That means next item's value by weight. Next item value by weight means we are dealing with item 3. So next item value by weight is 4. So it will be 4 into 4. So which come across around 69. Now let's say if the thief, if this node is further expanded, if the thief picks the item 4, already 9 is there, weight 9 plus 3, which is the item 4 weight is 3 gram or 3 pound. So if it is added further with 9, it will be like 9 plus 3, which is equal to 12. So 12 is greater than the knapsack size, which is 10. So no more further branching, so it will be called a dead node, because 12 is greater than capacity of the knapsack. But whereas here, if it doesn't choose the item 4, then it will be replicated as it is here. Weight will be 9 and V will be 65, and the upper bound will be 65 plus 10 minus 9 into Vi plus 1 divided by Wi plus 1. Now we are dealing with item 4, so there is I plus 1 will be 0. There is no fifth item, so that will be 0. So this will be totally 0, so upper bound will be 65. Okay. So you can see that if the thief doesn't pick item 4, then the total weight will become here knapsack. It can take up to 9 gram or 9 pounds of gold, and this is the value V, which is 65, and upper bound is also 65. Okay, so now and then if you expand this node, then here also you can see that the weight which is not optimal, that means weight is 4, and then further if you choose here 4 plus 3, which is 7, if you even pick item 4 here, so it will be 4 plus 3 7. So in that case also it is not meeting, it is not optimal, because here in this case we are getting 9 weight, we are getting weight as 9, but here we are getting weight as 7. So obviously this is poor solution, because always we want maximum element to be picked, maximum weighty element to be picked inside the knapsack. So and then now what you have to do, you have to see which are the nodes being terminated. Those nodes only will be considered for the final solution. So you can see that this node is terminated, this node is terminated, and here in the right subtree, if we expand, this will be the weight will be further lesser, because we are not selecting item 1 here. So already you are down, already the weight will be less. Okay, so obviously if it goes further, because it hasn't picked item 1, obviously the remaining subtree will not give you optimal solution. I mean, at least it will not give us the weight more than 9. So based on the terminated node, we can see that this node is giving the maximum weight and also the value. Okay, and upper bound is also 65. So this is the final result. Okay, and then this time complexity of this algorithm is this technique is to big O of 2 to the power n, considering that there are n number of elements. Okay, because n number of element means the levels of the tree will be n only. Levels of the tree also will be near about n, so it is 2 to the power n. Okay, so this is all about this algorithm, zero and knapsack problem, solving zero and knapsack problem using branch and bound method.
So it is the difference between branch and bound and backtracking. Both the technique uses similar kind of mechanism on function available for branch and bound, and backtracking also function available. But what and if you see the time complexity also, both both the techniques take exponential time. That means 2 to the power n. Okay, so and that means what, these both techniques have been devised from brute force method, and brute force method and backtracking slight difference. Backtracking branch and bound has slight difference, but this slight difference, many I have come across many students who doesn't know the difference implementation wise how, because implementation wise how to implement it. So the first thing is that branch and bound. The first thing is that backtracking consider all possible available methods. It consider all solutions available and uses DFS, depth first search. That means in case of backtracking, if you remember, subset some problem. Yeah, and then maybe this um, graph coloring problem that we are going directly through the path. We are reaching towards the leaf and path. That we see graph coloring. Try to see that whether the nodes are having different colors or not. I mean, in the tree, nodes should not be same color in the same path, right? I mean, immediate is just level wise they should color. If any two vertices, any two nodes is same color, means it's not giving the solution. So path wise we are going. So depth first definitely of backtracking. Okay, and both the techniques uses state space tree. Branch and bound, however, implements breadth first search. That means level by level we go. So two problems we have discussed. That is, one is this one is 0 1 knapsack problem, and then other one is job assignment. If you remember these two problems solutions, in case of 0 1 also we are seeing that level by level wise we are going, and in case of job assignment problems also, the tree we are moving from root to the leaf node level by level, not like path. We are not going deeper to the, rather we are going level. We go through depth first. Definitely branch and bound uses depth first strategy, and it also uses state space tree. So students, whenever you are going to implement backtracking, try to and through DFS using C or C++ program, and whenever you are going to branch and bound, try to see that if it is DFS. I thought this is quite a valuable information. Literature, I mean, in the standard books, these discussions are not. Okay? So thank you. So remember these 2 points: backtracking synonymous to DFS implementation wise, and bound to level by level.
both uses state space tree.